Hello dear student, this is Devang Shah from LJ Institute of Engineering and Technology from LJ University. Now in our today's topic, we are going to discuss about the synchronous counters. So far we have been discussing about the counters, and in our previous session we have discussed about the asynchronous counter. Let me start with a concept of digital counter. So you already know the definition of this counter, where digital counter is a circuit that produces a numerical count each time an input clock pulse makes an active transition, right? So if we are going to make a modulo 10 counter, whether it is a asynchronous counter or a synchronous counter, it will start the count from 0 and next stage is a 1, 2. Likewise, it will go up to count 9, and after count 9, see, it will automatically should reset to 0. So if both the cases are different, if it is a asynchronous counter, you can even generate or design a modulo 10 counter, as well as it is a synchronous counter, you can even design 0 to 9 count or modulo 10 count, right? So what does it mean? The output value increases by 1 on each clock cycle. So after the largest value, the output wraps up and back again to 0. So that condition is called the reset condition. So based on that, you can see all those counts start with the 0, 1, 2, 3, likewise up to 9, and from 9 again it will reset. So this is what the counter here. The main important signal in a counter is a clock signal, where clock, if you are going to apply individually to each stage, it becomes the asynchronous counter, and clock is same at each stage of the flip-flop or each stage of the count. See, this is called a synchronous counter. So again, this counter design is a kind of sequential counter. You have different options of inputs are available. From that, you will have two kinds of counters. One is called asynchronous counter. So the flip-flops are triggered with different clock, not simultaneously, but with the synchronous counter, the clock signal is simultaneously. You have to apply to each flip-flops, right? So by that way, we can also generate, or we can also design a modulus counter like binary counter, BCD counter, decade counters, same way ring counter, Johnson counter, up-down counters. We can also design it, right? Based on that, as such, it is a counter. So if you are in a state of 0, the next state would be 1. So if you are going to design a 2-bit counter, that means let's say your present state is 0, 0. So next stage would be 0 and 1. Likewise, you can have this kind of timing diagram. You can make from the counters. Based on that, there are different application of counters you can realize, like system clock, timer, and delays to generate a time and to generate a delay. You can make kind of timer, then watches, alarm, smartwatch systems, clock, counting events, memory addressing system. You can employ a counter design, frequency division. You can require a counter. So this is a simple diagram or a timing diagram. This is simple state flow diagram of 3-bit counter, and it start the count from 0, 0, 0, and it will go to 0, 0, 1, 0, 1, 0. Likewise, it will end with 1, 0, 1. So we can have a kind of 1, 0, 1 is nothing but bit of 5, right? So decimal number is 5. So you can see here, this is a kind of modulo 6 counter. So it will start the count from 0, go up to 5, and again it will reset to 0. So based on that, we have a basic difference between synchronous counter and asynchronous counter. So from that, synchronous counter, all the flip-flops are triggered with the same clock simultaneously, while in asynchronous counter, the different flip-flops are triggered with a different clock, not simultaneously, right? And the synchronous counter is a faster than the asynchronous counter, that particular operation. Same way, the asynchronous counter is slower than the synchronous counter. Synchronous counter is also called the parallel counter, and asynchronous counter is called the series counter. Again, in a synchronous counter, designing as well as implementation are complex due to increasing the number of states, right? But in asynchronous counter, designing as well as implementation is very much easy. Same way, a synchronous counter will operate in any desired count sequence. Asynchronous counter will operate only in fixed count sequence like up and down, right? So what does it mean? Let's say if you want to design a synchronous counter, start from the 0, then the next stage would be 4, then the third stage would be 6, 8. Likewise, you can design a synchronous counter with this sequence. But in asynchronous counter, it is up or down. If you start with the 1, the next count would be 2, 3, 4, likewise. Same way with the down counts. Here, synchronous counters examples are ring counter, Johnson counter. In an asynchronous, I like ripple up counter, ripple down counters, etc. Same way in synchronous counter, propagation delay is this, right? So it is much faster than that of the asynchronous counter. Based on that, if you want to design a kind of 2-bit synchronous counter, your first job is to check whether the clock signal is simultaneously applied to all stages of flip-flop or not. Yes, you can see the clock signal. So this particular 2-bit synchronous counter is made up from the JK flip-flop, where both the inputs of JK flip-flop is 1, 1. So in our previous sessions we have discussed, if the both input of JK flip-flop is 1, 1, so each time you are going to have a kind of triggered output at Q and Q bar, right? So based on that, if we apply the same clock signal to this particular JK based 2-bit synchronous counter, see, this is a kind of synchronous counters where the clock inputs, all the flip-flops are connected together and triggered by the input pulses. So based on that, if you apply the truth table of JK flip-flop, if both the inputs are 1, 1, so always you have a kind of triggered output. So you can check when the clock, the positive cycle comes from first cycle of clock. You can observe here with the green timing diagram. You can see here clock comes with the positive H trigger, the Q bar goes to 1, right? And see, the Q0 goes to 1 and Q1 is still it is at a 0 level, right? Because this is what it's going to trigger the your output. So in that way, see, you will have a Q of 0. See, you can see the pulse during the clock, it becomes 1, but Q1 will become 0. So from that, you can have a kind of count. It's from like first before the clock, the count is like 0, 0, then it becomes 0, 1, then 1, 0, and then 1, 1. You can see like that way throughout this particular clock cycle. So to 4 clock cycle, see, you can see here kind of down counter as well as up counters. Within the same diagram, you can have both the signals like with the clock signal, in one case it is a positive, and another case if it is a negative. You can realize both the kinds of up and down counters. Like you can observe the waveforms of Q0 and Q1 likewise. The first one is like if you start with 0, 0, 0, 1, then 1, 0. So you can see the first one is like 0 and 1, then 1 and 0, then you have a 1 and 1 at third clock signal. Again for a fourth is you will have a 0, 0, right? So this is a kind of up counter. If you talk about the down counter, you have to see this particular timing diagram in a reverse manner, right? So this is what up and down counter. Based on that, you can further discuss about the 3-bit synchronous up counter, where you can have a complete circuitry, which is this time it is made up from the D flip-flop, right? So here triggering has its own importance, where it's always with the application of logic 1, it will trigger the output, right? So trigger the output means the previously if the output is 0, this time it becomes 1. So it's continuously kind of inverting waveform is going to give. Same way in our previous example, you can see the timing of Q0 and Q1. You can again observe the sequence of Q0 and Q1. Both are completely inverting each other. So for a first clock cycle, if Q0 is 1, the another second clock cycle Q0 becomes 0. Right? Like that way, it will toggle the previous output by that way, right? So again, in this particular 3-bit synchronous up counter, you can see the design, and this is a kind of universal design where you can observe both. When M is equal to 0, it has an up counter, and when M is equal to 1, it becomes a down counter. So this is a kind of universal counter where you can have both the operations up and down counter. The principle is same. As such, you apply the 1 to the T flip-flop, see, output always becomes triggered, right? So output always becomes toggled. So in this toggled condition, you can observe the Q1, the first stage of Q1 when M is equal to 0, Q1 is 0, Q2 is 0 and Q3 is 0. So this is an up counter and the next count will be 001, 010, 011, likewise up to 111, right? The base part is that you can see here and you can observe here the kind of clock signal is same for all the cases, but here Q1, Q2 and Q3 you can again observe the timing diagram which is completely toggling at each application of clock signal, right? At each cycle of clock signal. Same way, if you take m is equal to 1, it will perform a down counting, right? So this design is completely easy. We are not much going into design. Again, if you can design a kind of 4-bit synchronous up counter by that way. See, the clock signal is again same, and this time we are again going to take either J flip flop, and same you can also take the T flip flop. You can design the same thing, right? The main part is that you have to apply logic 1 by that way. In each stage, see, the output will be the toggle of the previous output, right? So based on that, you have a kind of QA, QB, QC and QD signals, which is each stage output signal. If you're going to count it, see, once QA goes to 0, in another clock it goes to 1, and again the third clock it goes to 0. By that way, it's completely giving you the toggling output like 010101, and based on that you can observe the QB, QC and QD. See, all those signals are giving the like 0101 in this particular sequence, right? So you can check here for the clock pulses of 1 to 8. You can see, again observe the clock pulses of 1 to 8. From first 2 clock, see, the first clock when QA changes is completely giving the toggling the condition. For QB, the second clock onwards, it's going to give you the toggling condition. QC, you can see after 4th clock it will toggling the condition, so it will toggle the condition. And for QD, after 8 clock signal, it will toggle the condition. So by that way, you can achieve up counter, and you can see the count values are 0, 0, 0, 0. This count will become 0, right? So you can see at the bottom of this timing diagram where all the sequence of counts is like 0, 0, 0, 0. Next count would be 0, 0, 0, 1. Third will be 0, 0, 1, 0, and then 0, 1, 1, 0, 1, 0, 0, right? So from that you can see the counts start from the value 0. Next stage is 1, 2, 3, 4, and likewise it will go up to 15. Since it is a 4-bit synchronous counter, so in another way, this count is called the modulo 16 synchronous counter, where it will count from count 0 and it will go up to 15, right? Now after 15, the output must be 0, right? So it will reset to count 0. Based on that, see, that particular implementation you have to do with the help of logic gates, and this is very important part. Why? Because clock signal is simultaneously we are going to apply to the synchronous counter. So based on that, you can see there are 2 AND gate we have connected to we have connected after the second and third stage. You can see properly where the inputs of this is like JB, or in terms of the output is QA and QB. It's ending, and that ending output we are going to connect to the third stage of the JK flip flop. Same way, the output of this QA, QB, and the output of QC again we are going to ending, and that output we are going to connect with the fourth state of JK flip flop. So this terminology you can also design with the help of Kmap diagram, and from there you can be able to deduce same thing with the help of Boolean functions, right? Now this is again a kind of 4-bit synchronous down counter, and this particular the down counter is going to first start with the 0, then it will give you 15, count 14, 13, 12. So it will start in a way, it will start with the 1, 1, 1, 1, then 1, 1, 1, 0. So that's a 40, and then it will go up to 0. Again, after 0, it will reset to 15, right? So this is what a kind of down counter, and that circuit is also given to you. Again, everything is just reversed in that form. You can realize a kind of 4-bit synchronous down counter with the help of JK flip flop. Same you can also design with the help of T flip flop. Right now, in this case, you can discuss about the kind of advantages of synchronous digital counter, where it operates at the same time because the clock signal is same. It has no associated propagation delay because clock coming in the simultaneously. So the propagation delay is obviously very less. Operation is faster than with the asynchronous counter. It's easier to design than the asynchronous counter, and because of the count sequence is regulated by logic gates, the possibilities of error are reduced. So this is what the advantage is. Now simultaneously we have also discussed about we have to also discuss about the disadvantage of disadvantage of synchronous counters is like performing this task necessitates a significant amount of additional logic is required, because additional logic gates you have to apply, you have to connect the digital, the circuit becomes complicated and the number of states increases. Because it's a synchronous counter, clock signal is same, so you have to, your logic is again based on the boolean function, so you have to add extra logic gates. A single common clock pulse drives flip-flop in a asynchronous counter, sorry, a single common clock drives flip-flops in a synchronous counter, and the compared to asynchronous counter they required more components and hardware. Obviously this is what the requirement is. So again, we learn about the application of synchronous digital counters, where in which particular application we are going to use this kind of synchronous counters. We are using in a control of machine motion, motor of RPM counter, and encoder for rotary shafts, pulse generator, or digital clocks. We are using it in our smartwatch. We are using this kind of synchronous counter. Digital clocks, alarm clocks, we are using this kind of synchronous counter. So here we learn about the design of asynchronous counter as well as the synchronous counter. So mainly they are nothing but based on the flip-flops in a way at the design of registers, right? So thank you dear students, thank you very much.